You are attending a multi-fan blower door testing webinar.
And your presenters today are me, Mike Barsick.
And me, Burke Reeve. And we are both from this place called Southface.
Southface, we are a nonprofit organization based in Atlanta that does a lot of building science-based work on energy efficiency and green building. This program is, this topic is presented as part of a multi-year grant effort called the Advanced Commercial Building Initiative, or ACBI, and we have been doing quite a bit of research on small commercial buildings and how they use energy, and in this case, how they leak. And we want to share our experience. We've tested probably pushing 50 light commercial buildings over the last two and a half years, and we see this as an opportunity. If you are an energy assessor on homes, for example, this could be a great opportunity to expand your business into this sector. And also, if you're a designer, to learn where the problems are, or a contractor, learn where the trouble issues are and how to prevent unnecessarily leaky buildings. Anything you want to add to that? I'm looking for indication that our voices are being modulated, and it looks like we're good. So we're going to move on. Here's our contact information. I think that appears at the very end as well. So what are we looking at in this picture, Bert? This looks like a funny-looking house.
This is a commercial building, and it is being tested with multiple blower doors. So you can actually see at least, I think, 1, 2, 3, 4, 5 fans in this photo. So this is an example of a multi-fan, multi-point blower door test that's occurring on this building. And as we go a little further into the presentation, we'll explain what those terms mean.
Absolutely. Moving forward, there we go. Our organization, I think we've touched on that, and our website is southface.org, and we're going to talk more about the toolkits that are available on this particular topic is one of them, on infiltration in light commercial buildings. Here's a allowing us to give you continuing ed credit, course description, and learning objectives. And I think we've kind of hit the main aspects of that. We are going to touch briefly on the ACBI program and some of the other things we've learned, but today the real focus will be multiple fan blower door testing and some of the issues. And I know at one point we were asking, what's your level of familiarity with a blower door? Have you seen a picture of one? Have you tested a few houses? Have you tested a whole bunch of houses? Have you tested any commercial buildings? And have you tested a lot of commercial buildings? And I don't think very many people would say I've tested a lot of commercial buildings, because I don't know what the numbers are, but Burke, I would estimate we've tested 1 million houses in this country with a blower door. Maybe
that's a lot.
Not you personally or me, but it seems like it sometimes. But we have probably tested, at least at the beginning of this grant, less than 1,000 commercial buildings. And I say we, I mean all of us.
The industry.
The industry. So we're looking for, we're still kind of in its infancy. And a lot of times you hear about folks testing large commercial buildings, because that's a lot of times there's money to be had there. But this is a relatively untapped market.
That seems to be kind of the driver with this commercial building blower door testing right now. You might have someone like the Army Corps of Engineers that has a requirement, or another building owner that wants a particular spec to be hit. But by and large, I think there is not nearly as much testing of commercial buildings going on as there is, testing for single-family homes or even multifamily homes. And we want to make the case that there are reasons you might actually want to know about something like envelope leakage in a commercial building, in particular a small commercial building.
Yep. So we'll talk more about that, but first we're going to make a case for why are small commercial buildings something that we should be paying attention to, and then very briefly touch on some of the other things we've been doing in the program, and just a few lessons learned so far, which I think are kind of interesting, and then really hit blower doors. So we'll go quickly through this next little bit. The case for small commercial is really compelling in the sense of about half of all commercial buildings are under 25,000 square feet. about 2/3 of all commercial buildings are under, I'm sorry, I got that wrong. I screwed that up. It's 95% of all commercial buildings are under 25,000 square feet. 96% of all commercial buildings are under 50,000 square feet. But in terms of square footage, about half the square footage of all commercial buildings is under 25,000. And roughly 2/3 is under 50,000.
I wish we had a bar chart.
It would be really nice if someone could explain that in a clear way. But very compelling. They're in terms of number of buildings, there's very few buildings bigger than 50,000 square feet. In terms of square footage, they do represent, a big chunk, but
And I think part of the idea here is that it would be very challenging to test a 300,000 square foot building. You would need a very large piece of equipment in order to depressurize that structure. On the other hand, if you're talking about a 10,000 square foot office building, the same type of equipment that we use in a residential setting could be used to test that structure. And so we think there's some transferable skills here from the residential marketplace to the light commercial marketplace, and there's a whole lot of buildings out there that might potentially benefit from this type of testing and diagnostic activities.
Good teaser. I like that. So, and our target audience possibly on this webinar, you could say, was anybody that might be doing assessments on small commercial buildings, and also that does assessments on homes that, like Burke said, might see this as an opportunity. But also contractors and designers and anybody else, facility folks that are working in this market. I think there's lots of good stuff to learn here. And in terms of the usage of energy in small commercial, as you can imagine, it does vary. Unlike, houses are all pretty much a pretty consistent load or type of load. And commercial buildings are a little more different, depending on what's going on in there. If it's an office, it tends to be HVAC and lighting are probably about 3/4 of the energy use. Same for typical smaller retail. Mm-hmm. But then you get into anything with food related, then all of a sudden refrigeration becomes a much bigger animal in that process.
Process loads are a big deal in commercial buildings. What is happening inside the commercial building is definitely going to have a big impact on how much energy you're using. That doesn't mean there isn't value in trying to make a complete and relatively airtight thermal envelope.
No question about it. And then in our ACBI program, we've been through a process of doing research and really analyzing. We picked a dozen buildings that represented both new and existing buildings of a type of construction, kind of like what we saw on the previous page. We've done a ton of assessments. We've done deployment through some other programs of upgrades, and we're monitoring them. We're just trying to make sure it all makes sense. Great partnerships involved with this. I won't go through them, but this has been a great DOE effort. And then our overall approach has basically been to assess what we have, benchmark it. Let's analyze what the data is telling us, make recommendations, and try to project the savings. There's some great tools to help you do that have been developed as part of this. And then walk it through the process of the bids and the improvement, implementation, and then we found that verification has turned out to be a very big deal. Don't just assume because you wrote it down, this is how we want it to be, that it's going to happen that way.
Absolutely.
So that's probably been a really important lesson learned. So here's what tool have we mainly used for benchmarking?
Oh, what do you know? Energy Star Portfolio Manager.
A great, easy-to-use tool, and it gives you an energy use index, EUI, that kind of compares, or it takes your energy consumption annually per square foot. And so, typically you talk about kBTU, 1,000 BTUs per square foot per year. And then it's got other capabilities in it that can allow you to sort of check on how do you stack up against other similar buildings. For example, other office buildings in the southeast. How does your building compare?
And this is a great tool to track your own energy performance and then also be able to compare it against other similar buildings in your area. So if you're not familiar with Energy Star Portfolio Manager, I would say definitely a tool worth getting to know a little better.
Yep, pretty easy to use. And it's all based on real consumption. We did assessments of the buildings I mentioned. We did package recommendations, which is really a way of getting a more complete holistic upgrade as opposed to just going after the low-hanging fruit. You know, lighting and water is just usually low-hanging fruit, but you know, an HVAC or an envelope upgrade might be a little longer payback, but if you bundle it together, it's all acceptable. Like here's you know, a $79,000 investment that pays back almost 17 grand a year. That's a simple payback of less than 5 years.
Mm-hmm.
So, and then we've got templates for how to do reports and again, other tools, the process of putting out bids with good scope of work to help you get what you want. We've learned a lot about that. And again, the importance of going back and verifying it's been installed right. So to kind of summarize this, what are some overarching lessons learned? You know, we always, on the residential side, we say houses are systems. Well, so are commercial buildings. And sometimes you get people with sort of tunnel vision of how they view commercial buildings. And, you know, somebody's got a problem and they'll hire a sub and they'll come in and say, well, you know, my job is to fix just this. But they're not necessarily looking at it in the context of the whole building. We've seen people come up with very creative solutions that usually involve just glorifying the waste of energy. How many buildings have we seen, Burke? I know more than one, more than several, where there was a concern about sprinkler piping that had been retrofitted, that it could freeze, and so the solution was, let's just put heat into the vented attic.
It's an interesting approach.
It is definitely an interesting approach.
And I think you're right. It underscores the you know, issue that we often see, which is you've got buildings that have been around for many years. They may have changed in use and in occupancy over time. And so you've sort of had one approach to solve a problem or, you know, make the building perform better for one purpose that's been applied. And then a few years down the line, you see another one. And you end up 20, 30 years into the existence of the building, and you've got some strange things and some strange decisions that may have been made, such as, you know, heating a vented attic. Because if we added sprinklers at some point, we certainly wouldn't want those to freeze, so let's just heat the attic.
Well, and you made a good point, too. It's like a house may change owners, but the type of occupancy is still a residential occupancy. Commercial buildings, you know, the owners could change out. The new occupants are doing a very different task for very, very different reasons. And I say they don't own the space, too. A lot of times that's really the case, too, where they, you know, am I supposed to turn that off? Is that thing always supposed to be on, you know? And we saw a lot of stuff that was left on when it absolutely didn't need to be.
Mm-hmm.
And again, it's like, well, I don't live here. It's not my house. I don't own this place. I'm renting it or whatever.
Yep.
So,
and then perhaps often a trust in automation that may not be in your best interest from an energy use standpoint.
Yeah, that's a really good point.
We've learned that lots of times, especially in commercial buildings, if you have automatic lighting controls, you may need to go around and make sure that your outside lights aren't on in the middle of the afternoon. If you've got programmable thermostats, someone actually needs to look at how they've been programmed, because the schedules may have changed from when they were programmed 3 years ago. But
they may say HOLD, hold the temperature all the time.
And to your point, no one may feel particular ownership of that issue. You may have one facilities person who's putting out fires all day long, and they don't have the time to be proactive and go through and assess the building. Is this schedule correct? Are those lights supposed to be on? Should this be in setback?
And again, sometimes you get a situation where people using the energy have absolutely no feedback about the implications of what they're doing and the economic impact of what they're doing, because somebody else is paying the bill. They may not even be in that building.
Mm-hmm.
And so that's a missed opportunity. If you're a landlord, or if you're a lease space, you know, the focus of the landlord is just basically, you know, I don't want people complaining, not so much. The landlord doesn't usually pay the utility bills. Sometimes they do. But, and I say designers old school. I think what I mean is sometimes we have small commercial new construction or renovation projects where there really isn't a designer. There really isn't it could be contractor based, it could be a little bit of consulting on the side, but a lot of times not a holistic view of things. So that's, you know, and first cost is everything. Mm-hmm. So those are some of the issues. A couple other interesting things we've seen, you know, in terms of getting people to make improvements is the importance of rebates and how utilities are structured. You know, are you paying a flat rate? Are you paying a demand charge for your electricity in a commercial building? That can have a huge impact. Like I said, we saw a lot of equipment left on. Combustion safety is a whole nother topic and a whole nother toolkit. But what we saw, you know, I've been doing building assessments for 20 or something years, and I think I would say I saw more dangerous things in light commercial construction than I've seen in houses. LED upgrades has been an interesting one. Lighting, huge opportunity. The answer is simple, LED. But sometimes what you do or the path you take on LED depends on what you have. If you have, and your options are basically, I can take the old lights out and put in brand new fixtures that are LED. They're very efficient. They're going to last a long time. You're going to love it. Sometimes, though, you can say, I've got an okay fixture, but I'll just replace the guts of the fixture. I'll put a new LED driver in, and of course, LED lamps. But sometimes if you have fairly new fluorescent fixtures, you could consider, particularly as to do with the ballast, you can consider just relamping the bulbs with LED bulbs. They don't last as long, and you don't get quite the efficiency of the sort of the new guts, but it can be cheaper. So that's been an interesting sort of levels of things. You want to talk about any of the others on there? Just real quick.
Just looking down the bullet list, obviously vending machines are vampires. You may not realize it, but they're just sucking energy all the time in your building. So I think this is probably one that for a lot of people they may not even think about, but it is a relatively large energy load for vending machines.
And sometimes, and there is a huge difference between old inefficient ones and some newer ones that are much better. And sometimes we've seen cases where they were paying over $1,000 a year between energy and rental fees for a vending machine, and 4 people in the building would buy a Coke. And it's like, well, go, you know what? We told the owner, just get rid of the vending machine and offer free soft drinks to all your employees, and put it. They already had the fridge, of course, so it would have saved them, you know, $800 a year. So we've also seen interesting things with sprinkler piping and the issue of freezing. As we talked about how important it is to actually go back and verify the improvements were done correctly. And then ventilation, a whole other interesting topic. It is a gross assumption that to assume that because it's a commercial building, they are meeting commercial ventilation requirements.
That's true.
We've seen them underventilated and have huge humidity issues.
Overventilated and have comfort problems and energy problems.
Humidity issues.
And humidity issues.
and so it's been an adventure. So ventilation is a whole other fun topic. Okay, with that, we're ready to talk about blower door testing. And a couple things, because this says multiple fan blower door testing is what we're going to specifically talk about, but I want to make sure we're all clear the terminology. When we say single point blower door test, that usually involves just one fan, but it technically means you're just testing at one pressure.
And a reference point for a home that we're probably familiar with would be 50 pascals. So that is a single point, and that you're taking a measurement at that particular reference pressure or that single point.
In a commercial building, it typically the one pressure that we care about is 75 pascals. And then, not to confuse you, but it's possible to do multiple tests at a single point, because that adds to confidence in the number, and that's usually recommended. So you might measure your home 3 different times at 50 pascals, or your commercial building, 3 different times at 75 pascals. And so that provides some value, and in some cases there's a code requirement or performance requirement. But it is not as accurate and not as useful as a multiple point test or a multi-point test, which is what?
A multi-point test is essentially where you test the building, get this, at multiple reference points.
Oh, is that how you came up with that name?
So a good example might be you would start at, say, 75, and then you would work your way down to 25. And at 5 pascal increments, you might take a measurement, and therefore you would have multi-reference points.
Yep, and the advantage of this we'll see in a second is much greater accuracy and greater confidence in the performance of the building. To throw another multi in there is the word multifamily, and that's not a single-family residence or townhome. It's a bunch of dwelling units that are adjacent and have common walls, common ceiling, or common components that meet up against, in many cases, another conditioned space. And so there's really two tests there, an unguarded and a guarded test. We'll talk about that, and a term that we use called compartmentalization, which is sort of a form of that. And then also multiple fan, which means just that. We're going to be using more than one blower door, and then add the CFM through each fan, and that will give us the total CFM. Obviously, larger buildings, as buildings get bigger, in general, you have more surface area, more places to have leaks, and so you need more CFM to attain a test pressure. And with multiple fans, you can take a larger building and still get to a test pressure. So,
and you could test multi-fan single point or a multi-fan multi-point test as well.
Usually when you're if going to the trouble of setting up this many fans, you might as well do multiple point. And I think we'll make a good case for that, that there's some real value in a light commercial building of doing the multiple point test. And here's one of the reasons why. So you do not have to do this with software, but most people probably would use software to do it. And a lot of times the software will be automated. It'll help you through the process. But essentially, like you said, we're gonna look at the performance of this building. And this is a house, it looks like in this case. We're doing it at 5 Pascal increments. And it turns out if you, we're going to talk more about this graphing, but if you graph the log of the pressure against the log of the flow, you actually get a straight line. And they even claim that you could, for example, measure a house, do this, go back and tape up all of the supply and return ducts and repeat this test. And you could subtract at, say, 25 pascals, and the difference in the number would be the amount of duct leakage. We still prefer you measure ducts directly with a duct leakage tester, but it's kind of an interesting concept. And then the fact that you're doing so many data points and you have this straight line that's curve fit gives you a lot of confidence. And one data point might be the wind may have gusted, it might be off a little bit, but the straight line is usually pretty consistent. Now let's talk about multifamily blower door testing.
So multifamily testing, is probably something that a fair amount is happening of because of code requirements that would require most multifamily structures to be tested.
Or a program,
yeah,
an Energy Star or a green building program.
But we've noticed from our experience that the way you conduct that test really has a big influence on the results. Are you trying to determine leakage across the party walls? Are you trying to determine leakage from the outside? What are you really trying to measure when you go in and perform a blower door test on a multifamily unit?
So here you could be testing this middle unit right here, and it only has maybe, let's just say, 1 or 2 exterior walls here, this one in the front, and let's say there's one in the back, or maybe that's a conditioned corridor on one side. But very, very little part of the envelope is actually exposed to the outside. And but if you tested it with just one blower door, that would be an unguarded test. You potentially see a fair amount of leakage to adjacent units.
You'd be seeing basically total leakage across that unit's party walls as well as exterior walls.
Yes, exactly. And so if you wanted to make the other leakage go away, you just sort of need to surround the tested unit with the same pressure that you're testing it. So in this example, assuming there's no leakage to the corner units, which there very well could be, you need to have a blower door in each one of these adjacent spaces, and there it kept it, say, -50 while you test the CFM in the middle here. We've got some more detail on that. I personally did some testing, it was a good while ago, on some multifamily projects, and they were just interested really in the whole unit leakage. But we did a little bit of kind of comparison testing, and it's a little difficult to draw too many conclusions on this because sometimes you would see pretty manageable leakage across. Let's say maybe 20% leakage, but sometimes you'd see big leakage, 40-50% leakage across adjacent units. So it wasn't wholly predictable, unfortunately. And all I had to do just was with where the leaks are. Sometimes they're across the common walls. And I think, it was hard to sort of, ascertain a whole lot more than that. These, I believe, were just one story, or there were no conditioned floors above, so it was like a row of apartments, and you would test the middle one, for example. And we test it, and then we tested unguarded, then we tested guarded, and the difference in the reduction number would tell you how relatively leaky they were. Mm-hmm. So we have a coworker, or some coworkers that were involved in another project partnering with Oak Ridge National Labs, and they looked at several other units, and just to kind of share a little bit, this is their definition of guarded and unguarded. So this was a kind of an unguarded test, just testing one unit all by itself, and then a guarded test. This was there were actually 5 units, and they mirror imaged right across the central, stairway, breezeway, mirror imaged another 5. But they were able to test each unit individually, and then also test each unit with all the other units pressurized or depressurized. And it was interesting, and this was a good way to sort of tell the difference. And this is some of their test rig, and you can see they just had a blower door everywhere.
The high-tech bucket.
The high-tech bucket. But their results were pretty cool. And actually, as you might expect, let me go back to this. Units like 9 and 10 and 4 and 5 were on the top, and those tended to have, they tend to be the tightest, and they have the least amount of common surfaces, whereas units 8, 7, 2, and 3 probably had the most. And I think if you look at these, you can see.
And I think that's common in multifamily buildings. We tend to not think of the party walls as needing to be airtight the way we might think of an exterior wall or a ceiling.
And it's interesting, the code, is sort of backed off on that a little bit too. But we would argue, yes, absolutely seal it. You never know, that adjacent unit may not be occupied. It may be doing, stinky stuff that you don't want to breathe their air. So I would totally recommend. And fire, of course, is another reason. And this is a little bit of a segue into this topic. It's kind of the same thing. We use the term compartmentalization. And the basic idea is let's say you're testing a light commercial building, and it's got sort of 3 main areas to it. And ideally, you would open doors and have those areas all be the same, connected, and all be the same pressure. And if it was a lot of connectivity in a relatively tight building, you might be able to get by with either one blower door or one station of blower doors. Maybe you have 2 or 3 blower doors in one door frame. And the pressure in the building has good connectivity. Everything is about the same pressure everywhere. You can certainly you can do a test while you're running, or you can confirm that while you're running your test. But it's also possible that you get a building where there's just a wall, and there might be a door in one area, but it's a small door relative to the amount of CFM, or there might be no door at all and just no way to connect the compartments. And so in that case, you're going to need a blower door in sort of each of these 3 locations.
Zones.
And this we have to kind of say the software that we were using. So here I put these are really good blower doors, aren't they? Here's one over here, and here's one over here, and here's one in this sort of middle section. So the software that we were using by default would control each. You could make it control all 3 fans, and essentially what it would do is send the same amount of power to each blower door. And of course, if the whole building is connected, that's great. Each blower door adjusts up or down to give you whatever test pressure you want to test on. But when you're compartmentalized, what we found was it's quite possible that this front main section is really leaky compared to the other 2. And if you send the same amount of power to each fan, this one right here might not be at 75. It might only be at 60, and these might be at 80. And you go, okay, well, the average is 75, but that's not what we want. We want a pretty consistent pressure on the envelope, because that's what we're trying to test. So what could you do, Burke?
Well, in that case, you would probably override and adjust the power to the fans manually.
Right.
So you could send more power to the fans that you wanted to get up to 75 and adjust the other fans accordingly so that you can achieve that 75, if that's the number you're going for, pascals pressure difference in each of the zones.
So that there really is essentially zero pressure across the common walls, so to speak. The other option, which is kind of an interesting idea, is you sort of say, well, we're gonna let the red fan right here be the master zone, and everything, and it's going to be controlled to 75. And instead of saying, okay, try to make this between 75 and 0, we're going to say control the blue fans to where the pressure difference between the red zone and this one is 0. And so as the red zone starts going negative, it gets to minus whatever, then this zone will try to make the pressure difference across the wall be 0, and therefore it will also be 75. So that was those are some lessons we learned, and some techniques for how to control more than one blower door. That probably got deep in the weeds at the moment, but we'll come back to it. Hopefully people understand. Here's an example. This was a school we tested that, remember how big this school was? Like, yeah, I'll say around 22,000 square feet. Is that showing up? We have these were 2 classrooms, if I remember, with a kind of a dividing wall between them. And these buildings had a sloped roof, but they were foamed roof line, and everywhere there was that orange line right there, there was a firewall that went all the way up. So they really were 5 separate compartments. And we've also found when you get to a little bit more complicated buildings, it's nice if you can have someone that's a whiz at Google SketchUp, and you can kind of figure out, where do you want to put your blower doors. And in this case, I think it was pretty obvious. We had a courtyard here that we could have them all face. So communication amongst each of the zones is important, and we'll get more into detail. But anything you want to add on that? I think this is one where we kind of really learned the lesson about just sending the right amount of power to each fan, and later on we learned about the sort of the equal pressure trick. Okay, so there are several either codes or programs or specifications that involve commercial blower door testing, but it's still kind of in its infancy to some extent. Leading the way is the U.S. Army Corps and the GSA, General Service Administration, government buildings, federal government buildings that are actually being written in with a pretty good performance specification in terms of how tight they need to be. And a lot of credit goes to that. Washington State has apparently adopted this for larger buildings. ASHRAE 189 makes reference to this. LEED makes reference to blower door testing, I think in multifamily in particular. Our own Earthcraft Light Commercial program does have a requirement, a performance spec, which is the only one that I'm aware of that has it, possibly Earth Advantage. And then the Energy Code makes it a reference to it as an option, but most designers probably go prescriptive, which is basically if you build with one of these 27 common building materials, I'm sure it's going to be airtight.
But the good news is there is some of this happening out there in the market. And so whether it's a Beyond Code program or a state or federal standard, we are seeing more blower door testing happening in commercial buildings.
And whereas we've seen it sort of as an option in the residential world from the 2009 code, we know for a fact that that's not necessarily the same. A checklist is not necessarily the same as having to actually pass a test. So we're certainly finding that the test matters. So having it in a performance spec is really good. And again, I think we really have to credit U.S. Army Corps for kind of leading the charge on that. The terrific document that I would send anybody to, there's a lot of good places to learn more information. A terrific document is this one called Beyond Single Family Residential. And several authors on this, Terry Brennan and Gary Nelson and others. But I really want to commend Retrotech and Energy Conservatory. They have great training information. They have software. They have lots of ways to learn how to do it. And if you want a real basic one, single point setup and all that, then Southface has a couple. Southface YouTube channel, Southface blower door, 10-minute video. If you haven't done a blower door test in a while, you just want to get up to speed, it's a great way to do it. Duct testing, same kind of thing, Southface duct on YouTube. But this resource is about 100 pages long, lots of explanation of what you do. Great way to get you started. So here we are, Burke. Looks like I think this is an 1929 school we were testing.
I think that's right. No, it looks like we got about 10 fans and a pretty big crew out there.
I remember we had 10 fans, and it still wasn't enough to get to the test pressure. But after our improvements on this particular one, it was more than enough. I remember we did some impressive air sealing.
And so we've learned some stuff from getting out there and doing these tests.
Yes, we have. We definitely want to say follow a protocol. And we have a template of a protocol that we used for the study, that we used for Earthcraft Light Commercial. We are happy to share, or we're sharing that with you, but you can modify it. When you go to this prior document we were just looking at, it talks about U.S. Army Corps of Engineering based template, and that's what ours is based on. But even when you get in there, it gives you some options of how you want to do it. And so we looked at the options, we made a decision about what we thought told us the most information. And a lot of that has to do with what are you actually trying to test and what are you going to tape over. So that's a big deal. We talked about the importance of figuring out where you're going to put all your blower doors, and it's really helpful to have a set of the floor plans. If you can get blueprints, terrific. If not, what do we do? If it's an older building, the fire evacuation route,
fire evacuation plan, or have somebody do it in SketchUp.
Yep. Yeah, and that was useful. But it seems like you could at least get the fire evacuation little plot and do good things with that. We found it really valuable to, particularly on a bigger building, to have a pre-test meeting, and as we went through this, those meetings got faster, and we kind of knew more of what we were doing. But it was important to kind of assign everybody roles, because it's a lot of moving parts and pieces, and so everybody had this was a pretty big building. I think it was like 35,000 square feet, and so we were different multiple floors. People were spread out, and we found that I know one of the big lessons was walkie-talkies were incredibly useful, more so than cell phones. In this case, I know it sounds crazy, but walkie-talkies, because you can talk to everybody all at once, and you can also kind of have a listen mode where you're not picking up. So that was useful, some inexpensive walkie-talkies. People also had, when they were assigned to a location, they would set up the equipment or do whatever. Once we were doing the test, part of their job was to find problem areas in that zone.
And I guess that's a good point to say this type of testing can be done to get a specific number at a specific reference point to show that you pass a standard, but it's also a great diagnostic tool. And I think if you're out there trying to solve comfort issues and energy issues in a building, that this type of testing can really be done purely for diagnostic purposes. Where are the leak pathways, and what can we learn from depressurizing or pressurizing the building and investigating.
And I think we have the numbers for this building coming up later on, but if I remember right, it was over 60,000 CFM 75, and like I said, I don't think we had we didn't have enough capacity. We were able to plot the curve, but after we retested it, it dropped to less than 40,000. So it was very valuable. We also, I know it sounds silly, but it's really a pain to get out in the field and realize something doesn't work or you're missing a part. So the prep effort is certainly valuable. You want to lay out your equipment, make sure the batteries are good, turn it on, make sure the controllers work, and then and label it and put it all back, or pack it all up. Prepping the building for the testing. The test itself, once it's set up, really doesn't take that much time. We got to the point where we could knock out a pressurization or a depressurization curve in maybe 10 minutes, and that tells you a lot. The setting up for the test can be very time consuming, or sometimes not that bad.
It kind of depends, again, with these commercial buildings, you may have different types of activities. So you're going to need to determine in advance, do we need to be able to tape off a kitchen range and
or
kitchen hood in an existing building that's been in operation? So it's going to be greasy and disgusting. How do I deal with that?
Do it from the outside. I think is the lesson learned there. Yeah, we learned that on hoods. Now, if it's a brand new kitchen, we've taped some from the inside, but generally, yeah, from the outside is easier.
So there's going to be different types of buildings, and they're going to have different issues that need to be identified beforehand and determine how you're going to address them when you're actually setting up the test.
If it's your first time, you probably ought to play with the software a little bit just to make sure you can get it to do what you want. And again, that could be part of your day before prep. And then, of course, while you're doing this testing, is a great opportunity to find the leaks. And we're going to share some of our lessons learned on that as well. So the software, or as part of that setup too, is to again address issues with compartmentalization. And do you have common walls that you can get to? Sometimes in a strip retail, you might not be able to get the adjacent unit, for example. So I think the software, there's a picture of it there when it's in operation. It's got all these crazy things being plotted, but you can turn off things and see what's the building pressure or what's the fan pressure, and then each of these little green boxes is a period of time that we're recording data, and then this is kind of what we're looking. There's a baseline before and a baseline after. So this is all part of the software we were using, and it'll usually do the curve fit and graph the results. Speaking of sort of the shape of the curve, what actually the physics of what we're looking at, I guess, is this equation which says the flow, which is Q, is equal to a coefficient times the pressure difference raised to the nth power, which is an exponent. And when you do the curve fit, the software will tell you the flow coefficient, that's the value C, as well as the flow exponent. Usually, if you don't have you can only get this from doing a multi-point test. If you have a single point test and you try to go with it, they're going to assume some flow exponent, and that is not as accurate, obviously. So, if you plot it just flow versus pressure, this doesn't really tell me a whole lot. And the shape of this curve is correct, but it doesn't provide a whole lot of value. But you could, get the value of the leakage at 4 pascals. And why 4 pascals?
That might be more of a natural state.
Yeah, sometimes people say 10 pascals, 4 pascals. It's sort of a default. The building is sitting there pressure. It's different for every building. It's different every day because of the weather, but that's kind of like an average, pressure. Whereas 75 or 50 pascals is an accelerated, exaggerated pressure. A better way, as we mentioned, to look at this is instead of plotting that shape, is to go to the log-log graph, and it's a linear relationship in this case. So the log of the pressure and the log of the flow is a straight line, and a couple other things. This allows you to, now we have this straight line curve fit, we can easily predict how much infiltration occurs on this building at any pressure difference.
Exciting.
1 pascal or 100 pascals, whatever, we've got this great curve fit. And I can tell you're excited by it, but I am excited by it. This particular building tested out to be about 28,000 CFM at 75. And there's a little bit of uncertainty there. It tells us that. It also allows us to, I think if I click it blows up a little bigger, you can see the plot on here, what the performance is of the building. And if you look down here at 4 pascals, we're just, we're almost 6,000 CFM of leakage on this building when it's at 4 pascals. So that's the amount of infiltration on this particular building. I'm trying to remember which one. This is not that school. I forget which one this was. I think this might have been the health clinic. Anyway, so we have, so that's kind of the shape of the curve and the basic thing that we're trying to obtain. And we get this by plotting ideally 12 data points, roughly about 5 pascals each. And we usually kind of straddle between about 20 and 75 or so. The other thing we want to talk about is this concept of what do you do with that number. So in homes, many people, if you've done blower door testing, you're familiar with this term called air changes per hour at 50 pascals.
ACH 50. It's our sort of industry standard reference point. It's used in code, and it's used in beyond code programs as well.
And why are we not crazy about that term, the ACH 50? I mean, why air changes per hour? Well, not our favorite term.
If you think about the name, air changes per hour at 50 pascals, you're basically performing a test that says, if I ran this fan for an hour, how many times would I exchange the volume in this structure? And when you think about that, the issue is the larger the volume is, the longer you have to run the fan to create an air change. And so big volume structures essentially can have lots of leakage and still pass an air change per hour test because they get essentially an unfair advantage that comes from their large interior volumes.
Yeah, and the other thing is, you know, we're in a big room right now. There's a lot of volume in here, but the leakage does not occur through the volume of the building. The leakage occurs through the shell of the building. And when we say the shell, we mean the square footage of the exterior walls, ceiling, the floor that basically represent your building thermal envelope. So the leakage through the shell is really what matters. And if we normalize blower doors, instead of talking about air changes per hour, if we say the leakage per shell area, it's a much better metric. And we can use that metric for any size building. We can do 1,000 or an 800 square foot multifamily dwelling unit. We can do a 5,000 square foot house. We can do a 50,000 square foot building. And we're basically saying the amount of leakage is allowed to be greater on a bigger building, but only proportional to the surface of the shell, not proportional to the exponentially growing volume.
So this term, ELR, is envelope leakage rate. And at 75, so that's our commercial sort of standard test reference pressure. And what this term tells us is what is the leakage across that building's insulated, airtight, theoretically, thermal envelope.
And the envelope leakage ratio is a term that we use. Some people just may say CFM 75 divided by surface area of the shell, but it's the same thing. And I forget that something to that effect is what the U.S. Army Corps references. It's what the 2012 and after IECC commercial code references. So this is the standard way of doing it in a commercial building. And frankly, it's a better way of doing it in the residential world as well. We use ELR at 50 for our residential green building program. The more interesting thing, so we tested probably close to 50 buildings. And when we went into this, we had been testing a few in our Earthcraft Light commercial program before this study. But we kind of wondered, you know, how does our program compare against an average building? And is there any kind of a correlation that you can predict what an average building is going to be?
By age, by what type of materials it's built out of, by how large it is, by what type of activities are happening in it. Do these tell us anything?
Can you just say, oh, that's a CMU building with a metal roof. It's going to be relatively tight. It's going to be a half an ELR or something. And we kind of hoped that maybe there was some sort of a great correlation. You could just look at a building. And was that the case, Burr?
Unfortunately, no.
Unequivocally, no. There's the spread of, and we'll look at the data, was all over the place. And I mean, I wish that wasn't the case. But the answer is, it just depends on how leaky the building is.
So what that means is you got to test. If you want to know, you have to test.
And so is there a baseline for a, quote, average building? And, you know, how does that compare to an effort where you're really trying to pay attention to the thermal envelope? I would say yes, there is, but there's just a lot of spread in the data. And then, was anything predictable? And I think we would say yes here. We did find, where did we find problem areas? And it's stuff that you might expect.
Yeah, it is the intersection of two planes. So a roof and a wall intersection, quite frequently you'll have issues there. Anytime you change building materials, so you go from a block wall to a frame wall, you're likely to have an issue there. Anytime you change the location of your insulation and air barrier. So we've got exterior foam board on this stucco block wall, and then it transitions to cavity insulation on this frame wall. And oh boy, now we no longer have an alignment of the air barrier and the insulation, so we no longer have a complete thermal envelope.
Yeah. Lots of interesting things. We also found that if the local code jurisdiction tended to enforce fire code when the building was built, that tended to really help on air sealing. We actually saw intentional air sealing. If it was ignored, then we saw a lot of leakage. So that would be a factor at least in predicting. But I remember there was it was kind of neat. We tested 2 block buildings that it just happened. One was in North Georgia, one was in Atlanta, and we tested them within a week. And they were roughly the same square footage. I'm going to say around 4,000 square feet. You helped on one of them, and one of them came in pretty tight, and the other one came in unbelievably leaky. And a lot of it was because the leaky one had undergone some renovations in its life. Lots of holes had been busted into the CMU, and lots of leak paths. But unfortunately, you can't just say, oh, it's a block building, it's going to be tight. That we could not recommend you would make that assumption. But we did find, here were some interesting places that we saw problem areas, and these correspond to some things we were talking about specifically. Again, anytime you had corrugated roofing that was joining up with more corrugated roofing or a supporting wall, just the three-dimensional texture of that tended to lead to really interesting leak paths. So here's a few. We have a couple applications that we want to show. And the first one was, I believe, a historic building.
It is. This is a project we worked on here in Atlanta. This is a blower door test, and what we are doing is diagnostics at this stage. We are positively pressurizing the building, and then we are using a theatrical fog machine, essentially, to identify where a leak path is. And as you can see, on the inside of the building, one of our colleagues is blowing the fog into this utility chase, and it is leaking out on the exterior of the building, and it's leaking sort of down low where they're shooting the fog. It's also leaking up high at the top of the building where there's some conduit that comes out of that utility chase. So this is a real common air leak pathway where something runs from the outside of the building to the inside of the building, and where the penetration in the wall is, where the hole is hidden. It's not on the finished face of the interior. It's hidden inside this chase. So this is just a classic unsealed penetration and air leak pathway.
And to do this test, if you mentioned, was we pressurized the building, and then and I think probably to about 75 or something pretty high pressure. There's nothing magic about the amount. The higher the pressure, the more likely you are to see the leak. When I advance, this was another interesting, we talked about the joint of, this was a metal building roof that had real problems with the way the metal roof joined up and it looks like in a valley. And our colleague, I forget what we did, like maybe we pressurized the building and our colleague had a piece of wood fall and hit him on the head or something above the drop ceiling or something. And there were these shims that had been tucked in there. And you can see they had tried to caulk this edge, which of course wasn't very effective. And as we pressurized the building, the fog was shooting out of that. One interesting thing about fog too is you kind of need a darker background to see it, at least with the white color fog. This is another interesting one. This building had several challenges to it, and we were at one point testing the ducts, which is what you see in the left picture, but this is not testing the ducts. We're pressurizing the building. We removed an access panel that allowed you to sort of put some fog up into the location up in the top here, and as that, you could see that fog basically dispersed out. The original design of this building was CMU wall with a flat, hard ceiling and ductwork penetrating that, and that was a disaster. Lots of leaks.
Yep.
They came back and foamed the roof line, which sounds like, okay, great, we solved all the problems, but they couldn't get access to some of these places, or they didn't access some of these places. And when we pressurized it, the fog essentially went out. One of the, I believe there was a structural, like a metal I-beam that or a metal box beam that penetrated, and that was not sealed at all. So huge leak pass, and it looks like it's just coming out of the roof itself, leaking out in the this unvented roof assembly. So excitement there. Here's an interesting one we found on strip retail with packaged units.
We have a rooftop unit, and you can see that we are inside the building applying some fog from the machine, and then outside it's leaking around where the unit has been set on the roof.
On the curb, yeah. And not sealed, obviously, in this case. And I think we saw that pretty consistently on a lot of packaged units, that was a leak path. This was one of the more interesting ones. And also you can kind of see our technique. We use that same little fog machine. We'll show you pictures of that. But we used a big extension pole, and that allowed us to sort of inject the fog right where we wanted it, and while we were pressurizing. And then this was a block building, strip retail again, had just fog cascading down from that roof to wall junction. That was a very common leak path, as well as this bump out here. You can see the leak at the roof to wall, as well as this bump out connection. What else did we see? Well, we had a neat chance where we tested 5 sandwich restaurants in one a day for a week, and they were all spread around Metro Atlanta. And
how many sandwiches did you?
we found some interesting leak paths. In this particular one, it was the parapet wall that was leaking. And it's a little fuzzy on this side, a little foggy on this side. And pressurizing it, and you can see it's actually leaking out of the sign up there. So
parapet walls are another just classic leak pathway in this type of structure, because they don't really get treated like they are finished spaces that are connected to the inside of the building. So they tend to not be fully air sealed, often not fully insulated, and they end up allowing for leakage from the exterior to the interior because they're not treated like a finished surface.
Yep, that's very well stated, and always look for those problems. So here, I just thought I'd show you. Here's our little, so our fog machine was that blue fog machine. I believe this brand we used was a Viper. It was a fairly expensive one, but a pretty nice unit that could put out a steady, constant stream of fog. So more than the $80 units. But you can still use those. This was just a really nice device. But then it gets heavy standing on a ladder trying to inject it up high somewhere. So we took an old exhaust fan that we found in the dumpster and just essentially put it right in front of the fog machine. And on the end of that, we connected a piece of 25-foot, 4-inch flex duct and an elbow at the top of that. And that allowed us to, with the extension pole, really put the fog where we wanted it. And it was a great little tool. The last one is kind of interesting. It has to do with this pressurizing the strip retail, and the roof membrane started coming up, and it started going to adjacent units. This is not the original building this is not the building we were testing. Nice stance there. But this actually pressurized the membrane, and then it flipped over into the adjacent, and the longer we kept it pressurized, it worked its way all the way down to the end unit there. So that was pretty fascinating. What is that?
Again, just mechanical penetration, stuff that runs from inside to outside. And here we're looking at some pictures of various attempts to seal
or not
such penetrations.
We saw a lot of that too, where it was just no sealing, not even an attempt. And when you had particularly split systems with a condensing unit on the roof, the refrigerant lines and electrical lines and thermostats and stuff had to get through. So,
and this is a classic leak pathway. I tested last week a multifamily building, and they had not sealed the chases that allowed the refrigerant line sets to run from the roof down to the air handling closet in each of the individual units. They also were running bath exhausts and kitchen exhausts through that mechanical chase, and we're getting 4,000 CFM blower door numbers on these, 1,100, 1,000 square foot units. Why? Because there's a giant chase open to the outside, all the way up through the roof of the building.
So the common culprits, I guess, even if you didn't do a blower door test, you could probably make a safe assumption that these are good places to go look for air leakage. We also, as part of the Advanced Commercial Building Initiative effort in the last couple of 3 years, we at the beginning chose a dozen buildings, and we decided to really, really study them in great effort and do energy monitoring. And of those 12 buildings, there were different types of occupancy. Of those 12 buildings, 5 were part of our Earthcraft Light Commercial program. And some were offices, some were retail, some were food, I forget all the different ones. But we blower door tested those. So the question was, how do those 5 sort of compare with the randomly chosen 7 others, which had similar types of occupancy? And that's one way of looking at the data. It's kind of hard to grab, and then you can see the ELR here. But a better way, I think, of looking at the data was this. So when you plot the ELR for each of these buildings, you can see the ones in green are the ones that were all built under this high performance program, and the ones in blue were ones that were not. And remember, we said, what is the baseline for just a random building out there? What could you expect for a light commercial building in terms of the ELR? And the answer is it's all over the place. The range was quite high, from low as almost 0.4 ELR to pushing 1.5 ELR.
And it's interesting to look at this because one you can see as a trend is that the buildings that participated in a program that had a focus on sealing the envelope consistently performed better.
Yeah.
So that tells you, well, it can be done. It's just a question of how much attention are you going to pay.
Yeah, I agree. And it was interesting that we had one existing building that was actually a little bit tighter than one of these buildings, and one of the and we were looking at the data for that, and it turned out this is a case where this particular building, this PA building, had an enormous, an exorbitant amount of wall surface area. I mean, it was a one-story building that was about 8,000 square feet, but instead of being just a rectangle, it was really a star-shaped, and it had almost double the wall surface area. So if it happened to have been a rectangle and less wall surface area, then its number would have shot up, and it probably would have been up, more in the pack, so to speak. But what we found was, and again, this was just a random sampling, not trying to draw too many conclusions, but the ones that sort of paid attention had about a 0.24 ELR, and the ones that sort of didn't had about a 0.8. And so you could say they were over 3 times leakier. And I think this is sort of restating some of what we've already claimed, but the idea that it's hard to predict this, but if you want a tight building, you really need to pay attention to the effort at design. You have to design where the air barrier is and where the problem areas are going to be, and make sure those get sealed. It is possible to improve existing buildings, and we had several buildings that we tested multiple times, and we found, again, an effort at paying attention with an air barrier yielded usually pretty good results. One of the questions that comes up is, what's the economic impact of making a building tighter? And the short answer to that is there's not a good tool out there. The modeling software tools that are using this, we used 3 different approaches, and they had kind of different, they were consistent in the shape of the curve, but the relative amount of improvement on average was about 10%. But we saw quite a bit of variation. So I would say there's some work to be done on that, on having good modeling predict good savings of what's the benefit of retrofitting. And I say savings of 10%, I think that's on heating and cooling costs. We also did a bunch of other buildings, and I think we grabbed, I think there's about 30 more buildings here or so, and again, the ones in green were part of a green building effort, a designed effort. The ones that were not were random. And how did those stack up? And it turned out, again, pretty similar kind of results, that if you didn't pay attention, it was about 3 times leakier, or just a random building was about 3 times leakier than if you did pay attention. So, it's not 1,000 points of data, but it is 40 or 50 points of data, and we're seeing fairly consistent results in that sense. That I think you could say if you pay attention, you're talking about a building that's a good 3 times tighter. Okay. All right. We also looked at an existing building and making it better, and what the impact of that would be. This was a dining hall that turned out originally to be pretty bad, and with effort managed to reduce it nearly 70% infiltration reduction. A place of worship that reduced it over 25%. The school, I think we mentioned earlier, was about a 0.9 and came in less than 0.58, 35% reduction. And that was really, the school in particular, there was one improvement. It was a multi-story building. One improvement was mainly to eliminate the vented attic space and foam the roof line. And that building is rocking it now. It's a 1920s original building. It's rocking a Energy Star score of 100. So
all right.
It got new mechanicals, it got new lighting, but it also got big time envelope improvements.
So I just thought it was interesting to point out the dining hall and the place of worship in this scenario were new buildings that were constructed and ended up with higher infiltration rates on the blower door test than they were targeting for. Right. So they had to go in and sort of do some additional improvements in order to hit the number they were trying to achieve. The school was the only existing building that was tested right. Sort of as is. It's been around, as you mentioned, since 1929, yeah. And then retrofitted. So I just thought that was interesting to point out.
Kind of targeted air sealing efforts in the first two.
Yeah.
That I think we would say we all learned.
And that was going to be my point, I guess, was to say with the dining hall and the place of worship, more attention could have been paid in the design and construction phase to hit these numbers, at the beginning. And they sort of ended up with spray foaming as a retrofit because their original design strategy
had a lot of flaws.
Yeah.
I would say the design had some things that could have been better, but also the detail of the way it was put together was, really they didn't pay attention, even though they knew a test was coming. So this is, great, valuable lessons learned. And again, not that many buildings have been tested, and so we're learning a lot, and it's fascinating stuff. I think that's probably enough said on that. The energy modeling has its own topic worthy of discussion. So let's talk more about the test. And again, I think some valuable lessons learned. This was a recreation facility, I think.
Looks like it.
Get floor plans, or at least get a plan. So
a map to work
off of. SketchUp was nice, and mainly SketchUp. You're going to need to calculate the shell area of the building, and SketchUp was really useful for that if it's a complicated shape.
Absolutely.
Cut up shape. If it's a rectangle, or you can do it by hand.
Having a pre-meeting, and in some cases it may even be worthwhile if you have not visited the building to go on site and sort of walk the building beforehand. So prep your team, whether you're doing a multi-fan, multi-point by yourself, or you got a crew of 10 people. You want to have a plan for that particular building. Where are you going to locate the fans? What needs to be taped off? What needs to be left open? And how are you going to run things when you get there?
And again, some of these tools are available as part of this toolkit for free. So we think it's very important that you've got a site contact there, because there's always a good chance that you could pop a breaker and need to reset that, definitely want to have access to that.
Or a mechanical closet that's locked that you need to get into,
tape something off,
et cetera, et cetera.
Yep. Signage around the building, I think it's best if you can do it when nobody's in the building, but you need, if someone is, it's valuable to have signage saying, you know, this door needs to be kept closed. If you need to come in or out, let somebody know. We can do it between test data points. And a very useful thing, and we have templates for this, we found it useful. We wanted to put the building back the way we found it. So we felt like it was valuable to either take a picture of the settings on the thermostat, or better yet, just log it and make sure you put it back that way. And if it's one thermostat, it's not such a big deal, but when you got 15 thermostats and you're trying to keep track of all of this, it is a much bigger deal. So I think that was another big lesson learned. Well, we could have a webinar about the challenges of masking up vents on commercial buildings.
It's true, but you know, you're going to have bigger vents. You're likely going to have outside air on these commercial buildings. You very possibly are going to have large exhaust fans. So you need to sort of make an assessment of, when I'm doing a depressurization test, what needs to be taped off. If I'm doing a pressurization test, there's different stuff that needs to be taped off based on how dampers would operate. So making sure you identify those things, and then you have the tools in place to actually do that.
Yeah, and I would definitely say, and you probably agree, that we have more, I would say I have more confidence in our depressurization numbers, because that tends to, if we're masking from the outside, it tends to suck the mask in. And you can tell, we visually saw some cases where the pressurization test, the masking was failing, or you could tell. So it was definitely more of a challenge to get a good data. Sometimes it was great and not a problem, and the stuff was easy to tape over. Sometimes it was much more challenging. Material-wise, we found it valuable to have masking tape, sort of the beige tape. Sometimes it's valuable to have gray duct tape. Sometimes that blue painter's tape was useful. We used...
So you want all the tapes?
Duct mask, the mask itself, the roll that you might use when you do a duct leakage test. And the other big thing was the 3-foot roll of...
Like carpet cover.
Yeah, carpet protector. That was particularly good for large, you know, outdoor flat grills or things like that. Packaged units have challenges. So definitely, and then sometimes we would cover it with a mask and then we'd reinforce it with diagonal masking tape, for example.
You're going to have to learn by doing. The taping is a challenge.
I know, but if we can help someone, then it will, all our struggles.
Here's a good one that we learned that's easy to do.
Yeah.
There's lots of times going to be door closers on these commercial doors, and rather than trying to take them apart and then put them back together, something like a piece of pipe insulation or a pool noodle, as strange as it sounds, is actually really well-sized. You set your blower door frame right up there, you know, try and keep it parallel.
Horizontal.
Yeah, to the top of the door frame so that it's not at an angle. You set it, and then you can fill that space with the insulation, like foam insulation tube, and then run a piece of masking tape over it. It seals really well, and you don't have to deconstruct the building.
And it really is, that proved to be effective. I mean, getting the frame to jam in nicely, there's some good tricks on that as well. Some are in that earlier document.
An extra crossbar.
Extra crossbar is certainly nice, but essentially we found if we ran horizontally, even though there might be a 2-inch gap or an inch gap or something across the top, the frame would stay in place if you got it in there tight, and then you didn't have to disconnect everything. It was great.
You want to put one fan per circuit. This is particularly important when working in older existing buildings. And what that means is you do not have enough extension cords.
And you also need to know if you're on the same circuit or not, because obviously, you know, you might plug into 2 different outlets that are on the same circuit. So these are approximate numbers. I believe that you know, you might be on, say, a 20-amp circuit, and a blower door on high speed might be 9 amps. And so you're like, well, 2 of those, that's less than 20. And you're right, you can actually sometimes do that and get it to work. But when it turns out when you throttle back on a blower door, and it's because of magic electrical losses,
it actually draws
power factor. It actually, might draw 11 amps when you're trying to run at half speed. So when that will and has tripped a breaker when you're running more than one fan. There's some tricks you can try to work around that, but the best thing is by far to get everybody on its own breaker. One of the tricks you can do if you've got 2 outlets in a room and you want to know if they're on the same circuit is if you can get one of those little pretty inexpensive, like a watt saver or a kilowatt, those little things that you normally plug in the wall and say plug in appliances, and it tells you what the watt draw is. So you plug it in the wall and you look at the voltage on it, and then you go to your other outlet and you plug in a blower door. You turn it on fast, you turn it on full, and you watch, and if the voltage drops down more than a volt, then they're probably on the same circuit. And if they more or less stay the same or doesn't drop, then it's probably on a different circuit. So that's a good little trick. Just some little details. You cannot. It's good to have some long tubing. Tubing can be a little adventure. You don't want to get it wet. If water gets in the tubing, it has a little capillary effect that can give you garbage readings. And the ends can get frayed. And what happened many times when we had a lot of people when we're doing a blower door test, lots of tubing.
Inevitably, somebody steps on a tube.
And it sends like a pressure spike or something to the...
Turns your fan off.
And the software gets confused and it shuts off the test. So it's important not to step on the tubes. Ask me how many times we've learned that lesson. We found our fog machine. We talked about that was useful. If you go to a place, and we're going to talk about how do you guesstimate how many fans you need. If you have extra fans, one of the tricks, meaning more capacity than you need, one of the tricks is, like you see in this picture, you can face one out and one in, and then when you switch from depressurization to pressurization, you kind of already, all you have to do is sort of pull the power cord off one fan and plug it in another, and connect the two, connect the gauge upright. But it's you don't have to physically turn the fan in a different direction, and that can save you some time. And other important things to have with you. Anything else that you would do? Oh, on the frame, how would you keep the frame from getting blown in on, say, a double door, for example? That you see that a lot, and this one had. I can't. Yeah, I think it has 2. Hard to tell. Maybe not. Maybe 1. But you have, for example, 2 doors that butt together, and you obviously, if you can lock one of them, that's great. Sometimes we found if you can put a little clamp, you can keep the frame from being pulled in. There's little tricks like that. Some folks put a pencil and a piece of tape, and they say that the duct tape kind of holds the pencil as the frame is pushing it out and keeps it from moving. So there's just some tricks. Sometimes it's just worth it to have someone holding it when you first start up and not have to blow the frame out. All right, so Burke, this was a building we went to visit. It was roughly 10,000 square feet of shell area, and I think it was, it was like 40 by 60, so about 5,000 square feet of conditioned space.
It was set up so that there were essentially 3 separate compartments, 2 retail units downstairs and 2 apartments upstairs that shared a common hall. So we knew at the beginning we would have to have a minimum of 3 fans in order to deal with the compartmentalization.
And then to guess how many fans you would need, I mean, you could try to take 3 and maybe have enough, but one trick is to sort of say, well, I'm going to assume it's going to be fairly leaky, and I'm going to use the ELR of, pick a number, 1.5, that's pretty leaky. I don't think we had anything leakier than that, but we had 1.45, or some number, pick an ELR, 1, and back out, knowing the shell area, back out how many CFM you need. And in this case, we backed out that we needed about 14,700 CFM to get us to 75. And then we always say, you can assume, I use just, it's a round number, about 5,000 CFM per fan. might be slightly less, but it's about 5,000 per fan. And then add 1 extra fan. Just because it's never a bad idea to have an extra fan. And if you have too much, you can do that double thing. So here I think we had 1 facing in, 1 facing out. Here we just had a single and a single. We wired them all together and ran the test. And these were compartmentalized too, so we had to pay attention to that. This is the back side of the building. It turned out, I believe, it turned out too that we had way more capacity than we needed, which was great.
Yep.
So, just thought I'd mention this, that technically when you measure, what you're measuring is the fan pressure with reference to the fan inlet side. And when you depressurize, the fan inlet side is usually where you're standing in the building. So normally when you depressurize, you just need, you know, a typical two tubes, 1 for building pressure, 1 for fan pressure, and your gauge is right there at the fan inlet side. If you were to flip the fan around and blow air into the building to blow up or pressurize the building, you need to run another reference tube that essentially is to the outside also, and that would be on the fan pressure side.
So that your reference is on the same side as the fan inlet side.
Yep, and I think the Retrotech equipment kind of automatically does this for you. It always uses that reference tube, but it's something to be aware of, and you know, just a little detail. One of the resources that we put together was a test protocol sheet, and I don't know if we can quite read it here, but I may pull it up or something. But it's a spreadsheet, and the spreadsheet is you know, trying to walk you through the protocol. And I think the basics are, you know, you put the information in, who's testing it, what's the address, what's the shell area, and so then it can calculate the ELR based on your number. There's also a test that kind of says, is today a good day to do the test or not, in terms of or do we need to make an adjustment? And the adjustment has to do with, do you have too much stack effect, too much temperature difference, or are you too tall of a building? So it'll do this little calculation for you. And you know, if you have a 30-degree temperature difference between the inside and the outside and a 40-foot tall building, then your multiplication of that would be 1,200. So this would tell you this is not the ideal test condition because of other factors. Wind, of course, could always be a factor as well. But you enter your temperature, elevation of pressure. A lot of this is also going to be entered into the software, but we found it useful just to have it in front of you. You can print this out. I always found it useful to have a printed copy that I could just scribble the answer on. Sometimes we would also jump out of the program and go fill in numbers on this, but I found it useful to have a printed thing I could write on just to keep my head thinking. There's so many moving parts and pieces. And you're going to do it prompts you to do, you know, the baseline, to do the depressurization multi-point test, to do the post-baseline, and we always wanted to get a single point number too, and then compare that with the curve fit. So the single point number we'd usually do first, get to 75, see what the number is, write it down, and then go around and look for leaks, then do the rigmarole, let the software lead you. And then same for pressurization, and it would kind of remind you if you need to make any adjustment to your test pressures based on what your original baseline was. Most of our baselines were pretty close to 0, but we had some that were, you know, pushing 20 pascals, so we would definitely need to, instead of, if you start off and the building's at minus 20 pascals, you don't want to test it minus 75, you want to test it minus 95 pascals.
It's good. Good math.
Did the math right. And so you want to get you want to induce a pressure of 75 across the shell, not an absolute pressure. It also had some stuff that we would do, and our goal was to tape over something one time and remove it one time, and not go back and retest it. So that's why there's a flow of the logic of this testing. First we did depressurization, then we did pressurization, then we did pressurization with the mask removed from different things. And then we flipped it around and did depressurization with the mask removed from different things. This would tell us information about our damper location.
Yes.
We also did some building pressurization just to see, with everything turned off, but nothing taped off. What is the building pressure? Turn on the air handler. What is the building pressure? Turn on the exhaust fan. What is the building pressure? And this would allow us to sort of follow a protocol. So all of these tools are part of the multiple fan testing, toolkit. And I think we have that open. I was going to just try to look real quick. And what you're going to get is the slides. The introduction just sort of walks you through what the tools are. What we call the field guide is basically how to do that prep. The equipment prep, the people, it's got signs in there, templates for signs, and so on. The data collection form is what I was just looking at, the spreadsheet. You can modify it if you want to change it. I'm sorry, I'd take that back. The data collection form is, let's open it and show everybody. But the air leakage test sheet is what we were just looking at. And, the data collection is just a summary that helps you make a note of what's in the building and what you might need to tape over and so on, envelope dimensions and things like that. So to me, the test sheet is valuable as well. There's some signage, and there's a template for a report. The application guide is the one that I mentioned earlier, the great reference, 100-page, and we're happy to include that as well. Go back to wrap this up here. Just to mention that we are involved in a lot of light commercial research and partnered on other programs as well. Better Buildings Challenge, and Earthcraft Light Commercial has a deep energy pathway that guarantees, I believe it's 20% reduction over at the AIA 2030. Other great resources to take advantage of, and again, more detail about the program. So we have a few other webinars that are out there you can take advantage of, and our acknowledgement to our whole team and a lot of folks involved in the buildings that we have tested and we're still testing. So
absolutely.
Anything you want to add? Any questions or answers you would like to provide? This is we call this the walk of shame when you get through the door, and this is about as uncoordinated as you could possibly be.
There we go.
So we'll also snow angels on the frozen roof of the sandwich shop.
Well, very good.
So thank you, Burke.
Thank you, Mike.
And
there's our contact info. If you need to get in touch with us, email and phone number. And I should say thanks to our coworker, Alex Powell, for helping us put this webinar on.
Absolutely. And hope you enjoy.
Thank you.